This problem is known as a combustion analysis, where we're going to find the empirical formula for a compound with an unknown composition using the data from a chemical reaction where it has undergone combustion and given us a certain amount of each of its products. We are given the amount of the reactant initially and then the amount of the carbon dioxide and the water that is produced. So first, consider that majority of the time in chemistry, your goal is to get to mole. And so in this problem, you want to get each element to moles. And the elements that we are dealing with are carbon, hydrogen, and oxygen, in which we don't know how much of each we have. In combustion, there's a reaction with oxygen gas to yield carbon dioxide and water. We are told that we have 5.52 grams of this compound initially, and then the products yield 12.12 grams of carbon dioxide and 6.619 grams of the water. And so now what I want to do is I'm going to use the carbon dioxide to determine how much carbon did I have to begin with. I'm going to use the water to determine how much hydrogen did we have to begin with, and knowing the carbon and the hydrogen will allow me to determine how much oxygen we also had to begin with. So I want to take first these two amounts and get them to moles of the element. So 12.12 grams of CO2. Bring down grams of CO2, the molar mass from the periodic table, which is 44, equals 1 mole of CO2. Now, 1 mole of CO2 contains 1 mole of carbon. And so this is how we get to mole of just the single element in the compound. We get 0.27545 moles of carbon. Okay, let's do the same thing for the water. 6.619 grams of water. 18 grams of water is equal to 1 mole. And then 1 mole of water contains 2 moles of hydrogen, because that too indicates there are 2 hydrogens in the compound, so it's a 1-to-2 ratio as far as moles of hydrogen. So this gives us 0.73544 moles of hydrogen. So the tricky part here is finding out how much oxygen is there. So the entire compound has a mass of 5.52 grams. And so because we know the moles of the carbon and the moles of the hydrogen, we can actually figure out the grams of each of these, subtract them from the total, and then we would know the amount of oxygen. So I'm going to put 5.52 grams. That is of my total compound, CXHYOZ. I'm going to subtract the mass of the carbon, and if we want to know grams from mole, then we simply take our moles, 0.27545 moles of carbon, and 1 mole is equal to the grams from the periodic table. So this moles times 12.01 grams would end up giving me the grams of carbon. And then I'm going to also subtract out the moles of hydrogen converted to grams by multiplying it times the mass from the periodic table. So this value minus this value minus this value gives me the value of oxygen in grams, which is 1.4690511 grams of oxygen. And we actually need to go ahead and convert this to moles because we want moles of all of our elements. And so if I divide this by 16 from the periodic table, then I would have the number of moles of oxygen, which is 0.091817 moles of oxygen. Okay, so now I know the moles of carbon, moles of hydrogen, and moles of oxygen present in my original compound. So I'm going to now divide each of the moles by the smallest, which is going to be this value, 0.0918157. So we're at the divide by small part of determining our empirical formula. So when I divide these two values, it gives me 3 carbons, and dividing these two values gives me 8 hydrogens, and of course dividing these two values gives me 1 oxygen. So our empirical formula is C3H8O, which is going to be letter C.